Now, we already learnt that exponential graphs have this really interesting feature in that their vertical dilations can be written as horizontal translations and vice versa. Well, log graphs, as you'd expect because they're so similar, have got that same feature except it's the other way around. Horizontal dilations can be written as vertical translations and vice versa. Now, rather than just memorising which way around these things work, it's handy to really think about why it happens. So if we look first at the exponential curve, if we're going to make a vertical dilation, then we're going to stretch it or compress it this way. Now, it makes sense that if we, let's just say we compress it so that all of the points on the curve are now half the distance that they were from the x-axis. Well, taking any one point and saying I'm going to move it down so it's half the distance away, it's going to be closer, there is another point on this curve that has that exact same x value. It's over here. And so because of the nature of this curve, the way that the y value is actually the same as the gradient, if we change the y value, make it lower, we're also going to be changing the gradient, and those things are in proportion for a curve like this. So it makes sense that shrinking it down this way is the same as just zooming into a different part of the curve that's further over. Whereas if you stretched it that way, well, there's no part of the curve that looks like that. You're changing then the proportions of it, and the proportions importantly between the y value and the gradient. Now the opposite will occur over here. Here, if we stretch it or shrink it horizontally, we're changing how close it is from its asymptote, just like over here, changing how close it was from its asymptote. So it will have the same effect. And if I take any point here, in fact, if I take all the points and say, all right, I'm going to make them closer by half, there's another point on the curve that's exactly like that. And the proportions of this curve are such that it's really the same whether we shrink it down or stretch it out. It's a lot like moving it up or down. Over here, stretching vertically, it's a lot like moving it left or right. Now, do you really need to memorise this perfectly? No, but it's handy just to understand why it works. Now, if you have, say, a horizontal dilation and you're trying to write it as a translation, you won't be able to do it. It won't hurt you to try, but you'll quickly realise that the algebra just doesn't work out that way and you can't actually do it. So some people just remember that there's some dilations that you can write another way, and they don't bother to remember whether it's the vertical ones or the horizontal ones. But if you understand why it's happening, I think that you're ahead. So here I've got two examples where I need to express an exponential and a log function as both a dilation and a translation of the basic exponential function and the basic log function. Now this is revision, we've already looked at these, but I think it's handy to look at the method for both because it's the same method and it stands to reason that we can do them the same way. We'll also be then able to see the horizontal and vertical parts playing off against each other. So how to start? Well, really you just need to fiddle with the equation until it looks different. So the first thing I can see that's easy to do here is I could rewrite it like this, and that's changing the y value from the original curve into y divided by 3. So that tells me that I've changed the y value, I've stretched it vertically, and the factor is 3. So I'll say this is a vertical dilation with a factor of 3. Now, how else can I do this? Well, we need to use those ways of writing any number as an exponential function or as a log function. So what I do is rewrite the 3 like this. Now, why did I choose to write it as an exponential rather than a log? Well, because the rest of the expression is an exponential, so I'm making it sort of the same. And so now I've got the 3 part and I've got the e to the x part. Now I'm multiplying bases that are the same, so I can clearly add the indices. So I've got x plus the log of 3. So this now looks like a translation. Which way have I gone? Well, it's plus, so I've gone to the left. And how far have I gone? I've gone the log of 3 units. Okay, this next one, similarly, we just have to rewrite it as many ways as we can think of. Now, I know that the multiplication and addition law for logs tells me that I can split this up. Whenever the number in here has factors, and this does, it's 3 times x, I can rewrite it as two separate parts like that. Do you remember this rule? So now this looks a lot to me like a vertical translation because it's just like this curve, except it's got this plus log E3 tacked on. And in fact, if I wrote these around the other way, that might be more obvious to see that this is sort of tacked on to the end. So this is a vertical translation, and we've actually gone up, and we've gone the log of 3 units up. Now, if I can do a vertical translation, that tells me I must also be able to do a horizontal dilation. Now, horizontal dilation changes the x values, doesn't it? Well, how can I rewrite this so that it's x divided by something? Well, 3x is the same as x divided by a third. That's a bit of a tricky one that we've seen before. So here I've got a horizontal dilation because it's the x value that's been changed. It's been divided by something, and the factor is what it's been divided by, and that is, in this case, 1/3. So you can see here, vertical dilation goes with horizontal translation, and vertical translation goes with horizontal dilation. They work back to front from each other.